This screencast goes through the second part of our 7.8 notes. It's on page 9 in your note packet. Keep in mind that this is about probability, and probability is in general a ratio, and that ratio is the probability of some event happening is going to be equal to a ratio. So for the now, I'm just going to write favorable all over total, because like we talked about yesterday, there's really 3 types of probability that we're going to be looking at. The first would just be when the favorable, or the numerator of your fraction here, would be the number of favorable outcomes over the number of total outcomes. And this is geometry, so we're looking at the 2 geometric models of probability as well. The first one we talked about was where we talked about the length of a favorable segment being in the numerator and the length of the total segment being in the denominator. And the last one that we're going to focus on in this class would be the favorable regions area over the total regions area. In general, this is going to be the ratio that we're going to be keeping in our mind. So if we look at number 2, it says Elena's bus runs every 25 minutes. If she arrives at her bus stop at a random time, what's the probability that she will have to wait at least 10 minutes for the bus? So for this one, we're going to use the second probability model that we talked about, so the one that has to do with length. So I don't think that this one is as easy to get as the NAT problem from the previous page in our notes, because this is, like I said, it's a probability model. So although this problem doesn't involve length, we can still model the situation with a number line and with length. So I know that Elena's bus runs every 25 minutes. So I'm going to first of all draw myself a number line that shows those 5-minute increments up into 25 minutes. So I'm going to say 0, 5, 10, 15, 20, and we're going to end our number line at 25. So the reason I chose to write a number line that showed numbers 0 through 25 is because let's say that Elena just missed her bus. So therefore, the clock starts ticking from 0 and saying, well, she has to wait another 25 minutes until another bus comes. And that's the total amount of minutes that she could possibly wait until a bus comes. So now I have to think about, well, where on this number line would she have to wait at least 10 minutes for the bus? Because that would be the favorable part of our fraction that we're thinking about. So I'm going to go through this step by step. If Elena just missed the bus, she's right here, where she's at 0 on the number line because there's a whole 25 more minutes until the next bus comes. So at this spot, she definitely has to wait at least 10 minutes for the next bus. If we go up to 5 minutes, it looks like now, since 5 minutes has passed, she has all of this time to wait for the bus. Again, that's at least 10 minutes. If we go the whole way to 10 here, she still has this 15-minute span to wait for the bus. So again, that's at least 10 minutes to wait for the bus. If we go up to 15, she has to wait 10 minutes until the next bus comes. So if we go up to this 20, then there's only 5 minutes left for the bus to arrive next, which means that she is not waiting at least 10 minutes for the bus. So she waits at least 10 minutes for the bus, all the way from 0 up until this 15-minute mark. So let me add that here. We've got from 0 all the way up to 15 minutes. So this green part I'm showing as a length. And the part that I'm leaving off over here is where she would not wait at least 10 minutes for the bus. So if I put this into my ratio for favorable over total, I'm going to write in my favorable now the length. So the probability of waiting at least 10 minutes is going to be equal to, in my numerator, I need the length of my favorable segment. That looks like it's 15 units over the length of my total segment, which was 25 units. And it looks like I can reduce that if I divide both the numerator and the denominator by 5. It looks like I get a 3 over 5. And that's the answer. So I want to talk about one more thing about how I'm writing this here. We say the probability of an event. So I can take out that word event and put in whatever the particular situation is. So I want to find the probability of Elena waiting at least 10 minutes. And I just wanted to talk about that notation right there. So the probability of waiting at least 10 minutes is equal to 3 over 5. So number 3 says, assume that a dart you throw will land on the 1-foot square dartboard and is equally likely to land at any point on the board. Find the probability of hitting each of the blue, yellow, and red regions. The radii of the concentric circles are 1, 2, and 3 inches respectively. So concentric circles just means circles that are in the same plane with the same center. So this looks like it would make sense to apply the area model of probability to this. So I know that my my probability ratio in the bottom of my fraction, it's going to have the total area. So the total area of my region looks like, well, it's a square, so I'm going to do base times height here, and that's 12 times 12. So that will be in the bottom of each of my probability ratios. Let's talk about the probability of hitting the blue region first. So that's going to be the area of the blue region, which looks like it's a circle, and it says that its radius is 1 inch. So we need the area of that circle for the numerator of our fraction. So it's going to be a pi r squared. So we've got 1 squared in our numerator, all over the total area, which I said before was going to be this 12 times 12, which would be 144. So it looks like our probability would just be pi over 144, which is approximately, if I use 3.14 for pi, 0.02 for my probability ratio. Now for the yellow region, the radius of that yellow circle is 2, but I only need the yellow region, so I need the area of that yellow circle, but I'm going to have to subtract off the area of the blue circle. So, can you guys see it if I write in yellow? It's kind of hard to see, so I'm going to write this one in black instead. So the probability of the yellow region would be, like I said, the area of the yellow circle, which is going to be a pi r squared, but now our radius is 2. But then I have to subtract off the radius, or the area of the blue circle, which would be a pi r squared, where r is 1 because the radius of the blue circle is 1. So we did that up here, which just came out to be pi. And then that's all still going to be over 144 because the total region's area is 144. If I do some simplification here, it looks like I'm going to get a 4 pi from this part minus 1 pi. So 4 pi minus 1 pi is going to be a 3 pi all over 144. So again, if I use 3.14 in my calculator for pi, I'm going to do 3.14 times 3, and I get 9.42 divided by 144, and I'm going to get a 0.07 if I round. Now, the last one, it asks for the probability of hitting the red region. So the red region, if I think about how I can find the red region's area, I know that I'm going to have to find the area of the red circle, but subtract off the area that I don't want, which would be the area of the yellow circle. So the area of the red circle has a radius of 3 inches, so that's pi 3 squared minus, now I want the area of the circle, the one that looks like it would be yellow, and I need to use that radius. So I've got a pi 2 squared. And again, that's all going to be over 144. So if I do some simplification in my numerator, it looks like I get a 9 pi minus a 4 pi all over 144. If I keep doing subtraction and simplification, it looks like I get a 5 pi over 144. And again, if I use my calculator, 3.14 for pi, I'm doing 3.14 times 5. In my numerator, I get a 15.7 divided by 144 is going to be, it looks like 0.12 if I round. So it looks like the probability for hitting the red region is the greatest. For number 4, it says to win a prize in a carnival game, you must toss a quarter so that it lands entirely within the circle as shown here. To find it says find the probability of this happening on one toss. Assume that the center of a tossed quarter is equally likely to land at any point within the 8-inch square. So I need this quarter here to land in this circle here entirely. So that means that the center of this quarter needs to land inside this dotted circle here in order for the quarter to be completely inside this blue circle that they're talking about. But the total region would be this square, 8 by 8. So that area needs to be in the bottom of my fraction. And it looks like my favorable region would be, like I said, the center of this quarter would have to land within this dotted circle here. So my favorable region would be this dotted circle here. Looks like it has a radius of 1730 seconds. So my area of total region is going to be this 8 times 8, which would be 64 inches squared. My area of favorable, it looks like it's a circle, so pi r squared again, so we have a pi. My radius squared now is going to be this 1730 seconds, so 17 over 32. It's my radius, so I need to square it. So I need my calculator to do some simplification here. I'm going to use 3.14 for pi. So this is going to be 3.14 times, if I do 17 divided by 32, it looks like I get about 0.531, and then if I square that number, it looks like I get about 0.28. So then if I go ahead and multiply that 0.28 by 3.14, looks like I get 0.8792. So my probability ratio, so the probability of this event is going to be equal to, I've got 0.8792 all over 64, which is about 0.014 if I round. So it looks like it's a pretty small probability to land that quarter entirely within that little circle there with a 1-inch radius.